Okay, so thank you very much again for this second opportunity for explaining something something really interesting to you. And this time we change from what I said before about three-way analysis to something that is probably more familiar to you because specifically Iranian chemometricians are applying multivariate curve resolution quite a lot in a really nice way. And I will introduce you a little bit MCR, but from different cases that you probably have seen during this school. And I will let me use the laser pointer. I will use a recap, or I will do a recap from what they have said before using near infrared data. And then I will explain one case in which applying MCR in chromatographic data is actually extremely important. Then I will explain you how to use multivariate curve resolution in process monitoring as well, in how we can model reactions, specifically an enzymatic reaction using ultraviolet visible data. And of course, since as Hadi said before, I mostly use these days hyperspectral imaging. I will show you two examples. One dealing with quantification of principal ingredient in pharmaceutical preparations, and another one about microplastic detections. And I like these two cases because, first of all, one of them is in near infrared, and another one is in Raman. But both of them are actually demonstrated to be really reliable models MCR on this type of data. And at the end, as usual, I will do some final remarks. So, coming back to what you already know, that is principal component analysis. Okay, imagine that we want to. Opa, I've lost the. Okay, can you hear me? Hello.
Yes,
Can
yes,
you hear me there?
yes.
Okay, okay, perfect. Because I thought I lost the connection. Sorry, sorry, sorry. So okay, let me again use the laser pointer. Okay, so let's revisit the principal component analysis. Okay, and let's say that we have this mixture of three sugars, okay, in this triangular design of experiments that actually is quite familiar, and this is the near infrared data. So we all know that if we make a principal component a model in this data, well, first of all, we have to check what is the variance for each principal component, and it turns that for the first two principal components, we have a lot of explained variance, right? So if we represent the scatter plot of scores and loadings, we have something on the screen that is quite familiar for us. First of all, we have the scores, and here we can see the triangle, the design of the triangle. And then we have the loadings that actually, okay, we can study what are the peaks that are in the positive part, negative part, and we can relate with the different sugars in here. Okay. But what is important for me is to show you what happens with multivariate curve resolution. In multivariate curve resolution, if we calculate a model with three components, this is the explained variance we obtain for each component, quite different from the ones that we obtain with PCA. But the most important thing is the visualization, what's going on here. If we look at the score plots that we obtain with MCR, well, we see that we still have this triangle, but now we know we need three components in order to visualize this triangle, okay? And the most characteristic is the loadings that actually resemble a lot the pure spectra that we have in this mixture. So I like this example because I use it quite a lot in order to compare both models, right? This is the PCA response, this is the MCR response. So actually, as you already know, PCA actually is constrained to the components to be orthogonal, and MCR is actually based on linear dependencies between concentrations and pulse signals. This is one of the main differences. Then actually, principal components are normally sorted in decreasing order of importance. In MCR, this is not the case. Okay. And the most important thing that with PCA, what we do is to explain or to visualize different sources of variability or variance we have in our data. And with MCR, we aim at offering real physicochemical understanding of the process that we are measuring. Okay, and actually, in both models, actually these two models are projections on the variable space in different way, and they are differentiated mostly because PCA calculate the components with orthogonal constraint, while in MCR we have a more open, more free system that is regulated with more natural constraints. Okay, so defining a little bit the multivariate curve resolution model. Actually, we all know that this model is following or is ruled by the fact that a signal normally is linear to a concentration. Okay, so actually, this in chemistry we have it in many cases. So actually, most of the cases, right? This is what we like, or actually what I like. No, linear behaviors. So actually, and I will go fast into this one. Actually, we can say that for each point in our data matrix that is composed by, here we have the measurements, the samples, and here we have the variables, okay, as usual. For each measurement here in each variable, we can postulate the equation of the signal is the addition of the signals of the components, okay? So, and this signal of the components is characterized by a constant times the concentration. So, if we extrapolate this equation to all the points in this matrix, we can arrive to our general model of MCR that says that the signal here can be decomposed, in this case, with three components, because it's the case of the sugar. It can be decomposed into the something called the pure spectra of one of the sugars times the concentration of that sugar in all the samples, plus the same for the next sugar, plus the same for the next sugar. So something that is extremely familiar for you is the equation of MCR. Okay, so actually points to consider that we apply MCR when we have the mixture of at least two pure components. Okay, so it's a technique for resolving mixtures. Okay, the spectra of the components are overlapped. Okay, there is therefore is likely not selectivity in that direction in the signal. Okay, and of course the signals are multivariate, and everything can be defined by this linear of the equation in which the target is to decompose our experiment into concentrations and spectral profiles. Okay, there is nothing new here for you probably because this has been seen before, and I wanted you to see another example in which we compare PCA and and MCR in a more practitioner way. Okay, so where can we use multivariate curve resolution? Let's start with one of the main cases in which you can apply curve resolution, that is chromatography. And I will show you again some of the same slides as before, but it's nice to remember that in the cases in which you are measuring with a chromatographic device that has the ability of recording one full spectrum uh, per elution time, that is, here you have one elution time, there you have the spectrum, in this case a mass spectrum. Then for each sample, you have a matrix already. Then we can create these three-way structures in which we have the spectral channel, the elution time, and the sample, right? So before we have seen that this is a typical construction in chromatography, and that there is an algorithm, there is a method that actually works very nice when everything is fantastic. But this, as I defined before, is not very typical in chromatography. We have the problem of the losing of the trilinearity. Okay, so I said that when this problem, that is, I'm going fast because we saw these slides before. When this problem comes to our computers, there are two ways of solving it. The first one is to align and do parafact, or the second way, actually there are two possibilities here. The first one was something called parafact 2 that we saw before, or the one I'm going to show you now is how to use multivariate curve resolution. And we all know that if we talk about multivariate curve resolution, alternating least squares, one of the reference groups is the group of Professor Tauler, Roma, and also Ana de Juan there in Barcelona. Okay, so what do we do with MCR now? Basically, what we do is to treat this three-way construction as if it was a matrix. So if we unfold this three-way array into a matrix in which here in the rows we have the elution times for each sample, that means this is sample 1, and the elution time for sample 1, sample 2, elution time for sample 2, and so forth. And here in the variables we have our wavelengths, our spectra. Okay, we come back to bilinear problems, and this data is bilinear. So actually, we can use multivariate curve resolution, and what we will obtain is an elution profile per each sample. Okay, and the spectral profiles of all the components here. So basically, it's doing something very similar to Parafact2, but with an algorithm that is completely different. Well, not completely, but it's different because Parafact2 is based on trilinearity, but with the flexibility of the elution time mode. But in this case, this problem of linearity is solved because we have actually unfolded. This is one of the cases in which unfolding is actually quite advisable in this direction, in the sample mode. Okay, so to show you how to use this MCR in chromatographic data. I have this example that's actually a little bit more complicated because we are talking about four-dimensional arrays. Okay, but let me explain. What we wanted to do is to quantify all the compounds, especially sesquiterpenes and cannabinoids compounds that we can find in cannabis sativa plants. Okay, so we decided to take some of these samples, and we were looking for things like THC and derivatives. So let me show you one thing, because what we did in this case is to use GC, GC, FID. That is, now we will have two dimensions that corresponds to gas chromatography. Then we will have a third dimension that corresponds to the FID, and we will have a fourth dimension because we will measure all the samples at the same time. So in this case, we have here the monoterpene fraction that actually, in this case, since we don't have severe overlappings and anything, it was pretty easy to quantify. But the problem, the challenging one, it was the cannabinoids and sesquiterpene area, in which there were areas in where we have severe overlapping, even though we are using one elution time and another elution time. That means two chromatographic systems. We still have coelution in some of the times. Okay, so basically, for each of these cuts, here we have elution time 2, elution time 1, MC channel, okay, MZ channel. So we can take this structure, and for each sample, what we do is to unfold, okay, and now here we have the MZ channel and the elution time 1, elution time 2 for one sample. If we have more samples here, we could unfold in the sample direction, having a three-way array, and that three-way array can be unfolded again in the elution time direction. So here we can apply MCR, and we will obtain our concentration profiles and our spectral profiles. And the only difference with normal, let's say, classical GCMS or GCFID is that now each concentration profile here can be refolded into the two elution times. Okay, so applying MCR here, what we will obtain is a set of pure spectra and a set of relative concentration surfaces. Okay, so just a couple of examples of what we obtained here in this area. Look at this. I think it's a beautiful example because in this area we had three elements, three compounds overlapping, and we were able to identify them and then to detect them into a library and to resolve the mixture here for all the samples we treated. Okay, and at the end We did the same for other intervals, and at the end, with all these scores, what we did is a normal classification model, PLSDA, for instance, in order to differentiate stuff in the planets. Another particularly nice interval is this one, in which we observe that there's also three elements, in which here we have one of them, then we have the other one, and we have a third component that is actually mixed with the other two. But we are able to resolve this sample, to resolve this mixture, and again the same. We were able to take these relative concentration profiles and then do PCA and PLS with, or PLSDA or classification models with them. Okay, so this is one of the classical cases in which you can use multivariate curve resolution, and it works really nice because the trilinearity problems are just skipped because we unfold in a way that all our trilinearity problems disappear and we just stay with a bilinear model. Okay. Another case that I particularly like because it's part of my PhD thesis, okay, is that MCR ALS has been used for many years in process monitoring or modeling reactions, okay? And what I'm going to show you here is an enzymatic reaction that is ruled, is governed by what is called a ping-pong mechanism, in which we have the hypoxanthine that is actually transformed into xanthine due to the action of this enzyme. Okay, and the xanthine with excess of the same enzyme is metabolized to uric acid, and actually in excess of this enzyme, this is metabolized to derivatives of uric acid together with non-absorbing products. Okay. The thing is that all reactions, this is a big typical reaction that occurs in our urine, and quantifying these molecules might be important. Okay, so the problem of this reaction is that the three molecules are catalyzed somehow by the same xanthine oxidase, by the same enzyme. Okay. The second problem is that the spectra are strongly overlapped together with the spectra of the urine that I will show you later, that is actually absorbing in all the wavelength ranges. And if we want to monitor this system, actually we will find that it's a complicated system to monitor because there are 6 constants. Okay, so basically what we did is to monitor this reaction with time. In here, we have a reaction in which we have hypoxanthine that goes to xanthine, that goes to uric acid. So we know that we have 3 compounds. Okay, and this is really nice because we can model this simply with MCR, as I will show you later. But we will have an additional problem, is the fact that these reactions occur in urine. And as you can see here, this is the same concentration of hypoxanthine plus urine. And here we see that there is an increase in the signal, but if we calculate the number of principal components or the number of components that we need to use in order to apply MCR, it turns that we only need 3 components, but we know that this is not true. We know that here we have 4 components because we have the urine as well. So this is one of the problems that has MCR, that actually this is what we call rank deficiency. Okay, we have a species that absorbs, but it cannot be detected because the absorbance of that species is constant through the reaction. Okay, so what we did is to solve it with something that we call matrix augmentation, and I will explain you later how. But in order to show you how we monitored these reactions, we use a stopped flow system coupled with a UVB detector. So here in one of the drinks, actually, we put the sample, that is a mixture of hypoxanthine or xanthine or uric acid in different concentrations. Okay, we did a really nice design of experiments there. Then the enzyme there, and at a certain moment we push, and these 2 fellas mixed in the cuvette. So we were able to monitor the evolution that we have there. And actually we did it every second for 160 seconds. So actually it was quite fast, the reaction. That's why we decided to use this system. With these concentrations, with these reactions monitored, what we did is matrix augmentation in the samples direction, okay, in which we have here different aliquots of standards without urine, and here we have the samples with urine, let's say the problematic samples, so to say, okay? So indeed, if we apply MCR here, we expect to obtain one concentration profile, that means one evolution profile for each sample, and the pure spectrum, okay? But the thing is that we have the problem here of the urine, okay, and also we have the problem that I didn't say anything, but we had the problems that the postulated mechanism was changing a little bit with the uric acid, okay. So what we did in order to apply MCR in this system, it was to use constraints in the concentration profiles. So the first constraints we use is actually saying what is the initial concentration of the components that we have at the beginning in the standard samples. Okay, only in the standard sample, because in the rest, basically, we don't know. Okay, hypoxanthine, xanthine, and uric acid. And a wonderful thing is that in those samples, we can tell to MCR that here, in these samples, since they are the standards, here we don't have urine. We don't have that signal. Moreover, we can use, actually, we can constrain these concentrations to follow this model. Because we don't know about the urine samples, but we know that this is an enzymatic reaction. So regardless the interference of the urine, these three needs to follow this system, okay? We did the same with all the standards. And the good thing is that we didn't know anything about those samples because, as I said, we prepared different mixtures with hypoxanthine at the beginning, with xanthine at the beginning, with uric acid, with mixture of both of all the components. Okay, so we didn't know these concentrations. This is what actually we want to calculate. But what we know is that those actually contain urine. Okay. So here, what we did is to apply non-negativity and unimodality, and we give as initial estimations the pure spectrum. So at the end, what we wanted to obtain is the pure kinetic profile in here. Also, we were able to optimize the constants in a hard-soft modeling way. This is what is called the gray models. And here, what we wanted to do is to quantify what is the concentration of these components at the beginning of the reaction. Okay. So also what we wanted is to obtain the evolution of the urine and, of course, the spectral profile of the urine. So how did it work? Actually, it did it pretty nicely. These are two of the standards, okay, and we can see we can define perfectly the reaction. And with the unknown samples, we were able to obtain all their profiles together with the profile of the urine that actually was not that constant, so it was moving up and down, but it's also due to the signal. And this is the spectral profile that we were able to obtain from the urine and also the rest of the compounds in the reaction. Also, as I said, we were able to obtain an estimation of the constants, and also with the one that we had to include in order to fit the reaction, because there was a problem with the reaction at the end of it. And especially what we were able to obtain is really good validated models of root mean square error and standard error for the samples at the beginning of the reaction. Okay. So actually, in process monitoring, as I said, MCR has been used quite a lot of time, and here I want to show you how to use MCR in hyperspectral imaging, because the bilinear law that we have used before, it can be used also in hyperspectral images, and hyperspectral images are just an image. That means a spatial representation of a scene in two dimensions in which for each pixel we obtain a spectrum. Okay, so we can say that for each pixel in one wavelength we can postulate the equation that we already know, For each pixel in all the wavelengths, we can still postulate the equation that we already know, in the sense that now we will obtain the pure spectrum, okay? And for all pixels in all the wavelengths, again the same model. Okay, so basically in a graphical representation, if we have this sample with three, let's say these three figures, okay, if we apply MCR here, of course there is a previous step of unfolding, and then applying MCR we can obtain the relative concentration of the components in each pixel together with the pure spectrum. And the thing that changes from before is that now this concentration can be refolded in order to obtain a map of relative concentration of the different compounds that we had in our sample. Okay, so let me show you one application in pharmacy. Okay, because this approach MCR works quite well in pharmaceutical tablets, because if we think a little bit, pharmaceutical tablets are just a mixture of very well controlled ingredients. Okay, so tablets are strongly regulated, so they need to say, or they need to actually have the formulation. Okay, and in this case, here what we have on the screen is a tablet of lorazepam, and this is lorazepam. It's an antidepressant tablet. So actually, many times when you go to the doctor says you have to take half of it. And one of the questions that came to us is that, okay, if you take half of the tablet, you will have half of the active principal ingredient in that half, or the distribution here is not really homogeneous. Okay, so we wanted to investigate that question, and what we did basically is to create our tablets in the lab. Okay, by using compression forces, we could create tablets with different concentrations of compounds, including lorazepam. And the challenge in here is that lorazepam is so diluted, that is 6% of all the tablets, is so diluted that it might be difficult to find pixels here that contain that information of lorazepam. So here we created those tablets that are the standard ones, and then we augmented with real tablets of lorazepam. Okay, so at the end, these hyperspectral images, since they are unfold, they are just matrices. So this is the matrix of standards, and this is the matrix of the pixels of real tablets. Okay, we put them together. Here we put them together and applying MCR. Let's see if we are able to solve that mixture. And well, it turns that the solution was really nice. I don't have here all the results, but I want to show you only the result for lorazepam. That at the end of the day, it was the complicated one, because remember that the concentration in total it was 6% in the tablet. So here, what we can see is maps in the tablets. These are actual tablets in which we can see the distribution of lorazepam in pixels. And here we can study the homogeneity or heterogeneity of that distribution. For instance, in this tablet, in which we have these spots in which there are no lorazepam, okay? And applying MCR, as I said before, we can obtain the pure spectra. And the pure spectra of these tablets obtained with MCR was this one. The thing is that we didn't use the pure spectrum of lorazepam as a constraint or as initial guess. This is just models made as free as possible, only with one constraint, there is no negativity in concentrations. And what was astonished for us is that the recovery between the real spectrum here in black and the calculated spectra in red was extremely high. And that actually is a kind of validation for us to know that, oh, yes, what we are seeing here corresponds to lorazepam indeed. Okay? So actually, what we could do is also now with these maps to calculate what is in the left and what is in the right. And we can see tablets in which there is a huge misagreement between what is left and what is right. Okay, so this is quite highly appreciated if we want to remove this tablet, for instance, from the production line, because we cannot assure that the left part of the tablet and the right part of the tablet contains the same amount of lorazepam. And as a last example, yeah, have 20 minutes, so that's perfect. Yeah, in 15 minutes. Okay. So as a last example, I want to show you what we did recently about finding microplastics in muscles. Okay, using Raman imaging. Okay. So we all know that plastics are a threat. So I will not start with amount of plastics and blah blah. We all know that they are a threat, and we have to reduce, reuse, and recycle. That's the only that's the only action or the main important actions that we have to do in order to eliminate plastics as much as possible. Okay, this is only what I wanted to say about this. But going to plastics, when we swallow a plastic of a certain size, normally what it does, the plastic is to go in and we eliminate them. But one of the problems that we have seen is that certain plastics of small sizes, smaller than 1 micron, they might have the ability that when we eat them, of crossing the stomach walls and be part of our tissue, okay, of our muscles. So actually, we wanted to demonstrate that. We wanted to see or to show that plastics, when they are smaller than 1 micron, when you swallow them, there might be a risk for us to incorporate them into our muscles. And in order to demonstrate this hypothesis, we cannot use human beings, obviously, but we can use muscles. Okay, muscles are really good at cleaning the oceans. They are able to filter liters and liters of water per minute, and they are very well accepted as sentinels for marine pollution monitoring. Okay, so actually, what we did is to go to the beach and to take mussels. And by the way, I always like putting this picture because this is our research center. Okay, so you are welcome to visit us there. So we did all this research in here. Okay, so we took some mussels, some quite a lot, and then what we did is to put them in controlled conditions for salinity and temperature, and we left them clean themselves. Okay, then we placed them during 4 hours in a tank in which we spiked that tank with commercial polystyrene particles of 1 micron size. Okay, and actually those particles, those polystyrene particles, they were actually fluorescent labeled, and I will tell you later why. Okay, so they were labeled with fluorescent dye, and we let the mussels to eat them basically. Okay, and they did actually. They did eat the microplastics, and then once after a period that we considered, we took them, we freeze them, and we actually created 20 microns thickness slides in this microtome. Okay, and these 20 microns thickness slides are very important. Okay, these 20 microns, and I will explain you later why. Then with those slides, what we did is to go to a fluorescence microscope in order to detect the plastics. And here you have tissue with these dots here, they are the plastics. Okay, but here we have a problem. Well, actually, we have two problems. Uh, the first problem is due to the fact that we don't know where the plastic is exactly in the volume of these 20 microns that we have cut. That's the first problem. And the second problem is that these might be plastics that have been induced or have been introduced by our cells due to cross contamination. Okay, if you work with microplastics, especially if you work with micro and nanoplastics, you probably know that it's extremely easy to cross contaminate your samples. So the fact of seeing a plastic here is good, is okay for us because we can see that there are some plastics, but it's not a warranty that that plastic has been swallowed and incorporated by the muscle because it can be these two things. The first thing is that we don't know where this plastic is, and second thing is that it might be a plastic that has been contaminated. So we needed a less invasive method, and that's why we decided to use Raman imaging. Okay, the problem of Raman imaging is that we really needed to know where to target. Okay, because for you to have an idea, I put here a €2 coin that has around 26 millimeters of diameter. We were scanning areas that are equivalent to 100 times 100 microns. That means that if you take this coin and we zoom in here, we can see that this area is almost the area of Vizcaya, that is the region where we are right now. Okay, so fluorescence was used for both things. First thing, to check whether we had or not microplastics, and second thing, to know where to target when we measure with Raman imaging. Okay? So with Raman imaging, we measure this area, 100 microns, but actually we used one of the best qualities of this Raman microscope, that is the confocality of the laser. We were able to actually focus the laser in the surface of the sample, but we were also able to focus the laser inside the surface. That means, remember that I told you before that this cut here has 25 microns or 20 microns. We were able to measure what is inside this volume without touching it. And this is fantastic. First of all, because we will measure this volume and we will know exactly where the microplastic is. And second of all, we know that if we find a microplastic that is inside this volume, it's a microplastic that actually arrived there because the muscle ate it and not because it was a cross contamination induced by us in the lab. Okay, so basically using this confocality, we were able to measure 15 layers from layer 0, meaning the surface, up to layer minus 15 microns in each of the samples. Okay, and for you to have an idea of the amount of data, for each sample, we measure many areas, but this is one of the areas. That is basically 16 layers. That means 16 hyperspectral images here for one sample or for one area measured. So each layer was an average 120, that means 100-ish microns, times 84 microns, times 1015 data points, wavelengths or wave numbers. So basically that for each of these layers, we have 10,000 spectra. So if we have 16 layers, we have at the end 160,000-ish spectra. Oh, it's here, the total amount, 161,000 spectra. Okay? So here it comes a playground for a chemometrician that is really nice, and we could think about complicated stuff because we have something that is really good. We know what we are looking for. This is the pure spectrum of polystyrene, and it's fantastic. But this is the pure spectrum of a pellet of polystyrene. So this is what happens when you measure in a real sample in which you have 1 micron or less nanoparticle of that polystyrene surrounded by organic matter that is actually highly emitting signal, like in this case, these are the carotenes in the surface of the muscle. So it was very complicated to find, or we thought that it was very complicated to find the microplastics in there. Okay, so actually I will not explain all the procedure because we will not have time, but I can tell you that what I did is using principal component analysis on an augmented matrix. That means all these 16 hyperspectral images unfolded, and SMV, and mean centering, to do PCA to find areas in which I might have luck and find some signal of the microplastic, and then after those areas being located, to apply multivariate curve resolution in that particular area on all the 16 layers using well as pre-processing baseline correction like weighted least squares and constraints only non-negativity. You could think, oh, you could impose also the pure spectrum of the polystyrene because you know it. Yes, we could have done that, but the problem is that, well, we tried, obviously, but the problem is that the signal is so poor that there is a little bit resemblance between this spectrum and what I am going to show you now. Okay, so this is actually one MCR ALS model in one of these areas. Okay, this is the surface of the muscle, and this is the areas in which we might have plastics. Okay, and look at the MCR model, and this is what I told you before. In black, we have the pure spectrum of polystyrene, and in red, what we found. The signal was so poor that we have these waves here that we were promoted by the baseline correction algorithm. Okay, but we could not solve this thing because the data is really noisy, and we have the problem that if we apply a smoothing before, we will remove signals from this data that might be important in order to find microplastic. So actually, we based our intuition, our validation in the fact that even though having bad signals for our microplastics, MCR was able to give us this peak, but also this peak. Also here we found some information, and also this peak is important in polystyrene detection. Okay, so with this, we have to look at the concentration profiles. Okay, so if we look at the concentration profiles of these areas here of the MCR models, look at this. This is layer 0, that means this is the surface, and this is layer minus 15. And look at this, we can see the concentration evolution from 0, 0, 0, and suddenly here in layer minus 4, that is 4 microns inside the sample, we have a maximum, and then it decreases up to 0. And this is amazing because it tells us that there is something there that has resemblance with the plastic we are looking for, but it shouldn't be there probably. But what it's telling us as well is that this plastic is not in the surface, so it cannot be a cross-contamination. Together, that the fact that we took this signal and we were able actually to create this a 3D video in which we could see the plastics, okay, in green. The red is the meat, okay, the tissue of the muscle, and here in the middle we have a hole. That hole is the stomach. And the stomach is fine to find microplastics. It's not fine, no? But it's logical to find microplastics. But what catch our attention is that here, in this part here, we also found microplastics. And this is not that normal because this is actually part of the organelle of the muscle. So here they shouldn't be in there. Meaning that actually we have demonstrated the hypothesis that, the muscle is able to eat these microplastics and incorporate them in the tissues of the muscle. And the thing is that this doesn't mean that you don't have to eat them. No, of course you can eat them. They are delicious, especially with tomato. But the fact is that if this happens to the muscles, this might happen also to us. And that's what is let's say, the scary part. So basically, you can see that with multivariate curve resolution, one of the main things of multivariate curve resolutions is that it's really versatile. Every time you have overlapped signals and you have an evolution, it's easy to apply MCR in some way to obtain information about the relative concentrations and the spectral profiles of the components we have there. So it's somehow easy to solve mixtures. Of course, it's a second order technique, so we can also make some calibrations in presence of interferences. Few samples are required to construct good calibration models. Okay, and using the constraints, it's easy to uh, make it more versatile for different cases. The main problem, and this is why I have a love-hate relationship with this method, is that it is not simple to use. Here, when I show you these models, okay, every element here should be optimized in the number of components, because here in the muscle, each area could have perfectly different number of components because we are in different areas of the muscle. So this needs to be optimized manually, so to say. Okay. Also, if you have a lot of overlapping in the signals, that's difficult to solve the signals. Okay, and we need to be extremely careful with constraints because since it is a so versatile model, we can apply a lot of constraints there. So at the end, we really need to validate what we are doing when we apply constraints to MCR. Okay, and and of course, I always say that it's really good in this type of cases. And we work a lot with food stuff, measuring near infrared in food stuff. And there, for instance, use of MCR is complicated because near infrared, you know, probably that it absorbs a lot of OH bands, and food stuff is full of OH bands, and that can hamper obtaining good results with MCR. But saying that, I really encourage you to use MCR on these cases, and I cannot live past the occasion of making a bit of commercials. Okay, here in this website, you can actually download a graphical user interface to apply MCR in hyperspectral imaging, apart from other models, and also something that Hadi said at the beginning. You can also find information about the International School of Geometrics that we are running this year in Copenhagen. That will be between 15th of May and 3rd of June, because later you have to come. If you do hyperspectral imaging, you have to come to Bilbao, because from July 6th until July 10th, we will have the International Association of Spectral Imaging meeting here in Bilbao. And that's all. I hope I have encouraged you to use MCR more.
Okay, thank you, Jose, for your inspiring presentation. It was very nice. So, any questions? No question? Comment? So there is a question here. Thank you for the presentation. I didn't understand why you didn't observe microplastics on the surface. Is it possible that this is due to the tissue cutting method?
Exactly, as well. Yes, it is. It is also one of the things that we wanted to avoid, but it's not possible to avoid. That let me just come back here. Okay, here we are. When we cut the plastic, when we slide, sorry, when we cut the muscle, we also had a lot of risk to have cross contamination due to the cutting, due to the blade, and we wanted to avoid that thing. That's I mean, we cannot avoid it. So in the areas here, let me show you. In the areas, in this case, we don't have any area, but we have cases in which we can see the plastic here in at the very beginning. That means at the surface, and then the signal decreases. So that for us is not a valid plastic, because that plastic is on the surface and it could be for cross contamination, or also, as you said, because we have induced that plastic in the surface, or even in the first and second internal layers, because when you cut, you make certain force so the plastics can go to those layers. So we found, and we have some cases in which we found plastics there in this 0, -2, and even sorry, 0, -1, and even -2 layer. If we find plastics in there, for us, this is not a valid case. Here I show you one example in which we found several cases, several plastics, but they were really well internalized, so there is no risk that is us inducing that 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 signal.
Okay, another question is thank you for your presentation. I have also a question. I was wondering if we could get the absolute concentration by having the set of the calibration in the case of hyperspectral imaging.
No, that's okay. What you can do, I mean, there is something that is missing here. Yeah. What you can do with MCR is to get relative concentrations. But then when you get these relative concentrations here, what you need to do in order to obtain absolute concentrations is a regression model. You can take all these solved relative concentrations and make a linear univariate regression model, and then you can predict the concentrations for the rest of the samples. Okay, so if we are talking about absolute concentrations, it has to go always with a regression model. In this case, univariate, because you already resolved with MCR. And it is even good because you do this regression model and it's easier to validate than if you don't do it. So with MCR, we only obtain relative stuff. Then if you want to go to absolute stuff, you need to pass through a regression model.
Okay,